If we have a liquid circulating in a recirculating system like this, possibly in a building heating system or some kind of process cooling system where the water or other fluid goes around and around and around in a circle, then our piping calculations actually get a little bit easier. If we write Bernoulli's equation from 1 to 2, we'll get the same thing as we got for our point-to-point calculations. If we write it from 1 to 3, we'll get the same thing as we got for our point-to-point calculations. But in fact, we can go all the way around the loop and include all the components and write Bernoulli's equation between location 1 and location 1. Just like we did with the point-to-point, except we'll treat that point and that point as the 2 points. So we'll wind up with Z1 plus P1 over rho G plus V1 squared over 2G equal to Z1 plus P1 over rho G plus V1 squared over 2G. We started here and we went all the way around the loop and added some energy with the pump. So we've got a delta HP term over there. And we took out energy along the way, so we're going to have minor loss terms and head loss due to friction terms. So delta HF and delta HM. Z1, P1, V1 squared are all the same at both locations. So that whole lot there and that whole lot there will cancel out. And we're left just that the head rise provided by the pump must be equal to all of the head that was lost, to friction, and to minor losses along the way. Now you'll notice that this recirculating system has pipe and fittings, which we know how to deal with. So we'll have delta HP equal to F L over D V squared over 2G plus the sum of all the K factors for the fittings times V squared over 2G. But what about these other components in here? These might be heat exchangers or tubing in a boiler or some other system that we don't know very much about. We would need to use K factors for those as well. We expect them to behave the same way with this V squared over 2G factor as anything else, and we'd need to know that K12, that K23, and that K34 for whatever equipment those were. So plus the sum K12 plus K23 plus K34, whatever those pieces of equipment are, times V squared over 2G. Where would you get the K factors from? Well, for the fittings, we're going to get those from a handbook. We'll look up and find out that for a 90-degree elbow at appropriate Reynolds numbers, we've got a value of, say, K equal to 0.4, something like that. And we can sum up the K factors for all of the fittings by going to the handbook or to tables in the text. For these other components in here, they may not be standard components. The only way that we'll be able to figure out what the K factors are for those is to have measured the pressure drop across these things or the head loss across these things under some condition and be able to back out K. So if we have measured delta HM and we set that equal to K times V squared over 2G, and we'd use the velocity of the inlet piping, then we can figure out what K is. K will be that delta H measured divided by V squared over 2G. So we can figure out the minor loss coefficients that go along with a particular unit. For instance, for K12, we'd measure the head loss from location 1 to 2, and we'd use probably V1 as our reference velocity. And we just make a note that V1 was the one that went with K12. So that's how we do piping calculations on a recirculating system. All of the Bernoulli terms fall out of the equation, but it's good to write it down anyway just to keep ourselves honest and remind ourselves that we are balancing energy as we go around the loop with the recirculation.